thing I'm really enjoying this year is the variety of talks talking about embedding. Always been a huge fan of embedding, and I think it's something that's very underutilized in this space. But anyway, so my name's Rob. I'm with the M365 security response team at Microsoft. And I'm going to be talking about some work I've been doing with detecting homoglyphs. All right, there we go. All right, so the first issue to deal with is what exactly is a homoglyph? So a homoglyph is a word where characters look like the characters in another word. So very, very common in cyber data. So heavily used for things like phishing. It's used for disguising command and control domains, credential harvesting. Pretty much any cyber attack that involves network data is highly likely to use some type of homoglyph attack. And one of the neat things about homoglyphs attacks is, unlike most attacks in this area, they're not really an attack on a computer. Homoglyphs are really an attack on the error correcting mechanism of the human visual system. So fun little space to work on, and have some help from my research assistants as well through this talk. But so homoglyphs can be fairly simple. You can substitute in this first example. RN looks a lot like M. You can substitute that as for the character M. Sometimes they'll add random sequences of numbers or letters. So like LinkedIn 123 instead of LinkedIn.com. Sometimes attackers will use entire English words to make it look like their domain is affiliated with something. Like in this example, you could have Bing Pro Services as opposed to Bing.com. So historically, there's been, this honestly hasn't been a heavily worked on space as far as homoglyph detection, which is a little surprising to me. But most of the traditional attempts that are in the literature for doing a homoglyph detection are doing things like doing n-gram comparisons between strings, looking at Levenshtein distance. And that's all extremely computationally intensive. Anytime you're looking at, an n by n distance comparison, that, you're not going to have a fun time running that on, a internet scale level of data. So one particularly interesting paper that I've seen dealing with this problem was put out by Hiram and some of his colleagues back in the day. And my approach is heavily inspired by their approach with a few little tweaks. But basically what they were doing was looking at, anytime you look at something like a image problem, if you're looking at, say, comparing two images, of course, the first thing most of us go to is convolutional networks. So in this case, what they were doing was using a convolutional network on a image of the entire domain string, feeding those into a Siamese network, and then, using that to find similar strings. I went ahead and gave that a try, and it worked decently. The one thing I observed was that the convolutions largely appear to be learning the number of black pixels in the image as opposed to, say, letters. And my thoughts are it's a great approach, but when you feed the images to a convolutional network, you're kind of making things harder than you really need to for the neural network. We already know that in a domain name, it's going to be a sequence of characters. So we know that we're going to have characters. Maybe we're expecting a little too much if we're expecting the neural network to figure out what characters look at from a larger image. So, like I said, I really like embeddings. Usually, if you can figure out a way to embed some data, you can do some really cool stuff with it. Because let's face it, most of math was created to model things moving around in space. or other physical things. If you can use the same analogy for your data, then you've got a whole lot of math that you can take advantage of there. So what we're doing here is, instead of doing a convolutional network over an image of the domain, instead you create an image of each character in the domain, and then you train a LSTM over those sequence of images. And that gives you the advantage of, you've kind of already, you're not making the model learn characters in a natural language on top of learning the image processing. So it makes things a little easier. And one of the nice things with this particular problem is, a lot of times for purposes of fairness or robustness, we really don't like our neural networks to be memorizing things, especially lots of details. In this case, that's actually an advantage. If the neural network is memorizing domains, then that's something that we can take advantage of. So, of course, the usual problem you run into with this is there is no data set out there with labeled data of homoglyphs and the domains that they correspond to. Fortunately, this is a really easy problem to generate synthetic data for. So in this particular case, we're using to train the initial model, used the Majestic Million dataset, which is a dataset of the most frequently referred to domains on the internet. It's fairly regularly updated by a group. It's, you can get it online. I believe it's a Creative Commons licensed, but it's a really good dataset if you're dealing with anything network related. And so homoglyphs being generated from legitimate domains, we worked with some subject matter experts who do a lot of work with homoglyphs and other similar pieces of data in the security space, and we created our own homoglyph generator. And we update it fairly regularly if we see new tactics for generating homoglyph domains. But this lets us generate a pretty much as much synthetic data as we want that will transfer over to real-world use. And this is basically a diagram of the network we're working with. You've got your series of images of each character, make those as big or as small as you want. I was working with 7x10 images. That's small enough to train fairly quick and still big enough to actually distinguish characters. Feed those into an embedding layer for each character. Those all go into an LSTM. Get your final fully connected layer on the output for generating your final embedding. And then you can the nice thing is you could put those embeddings into a structure like a KD tree, which will make your queries way faster. If you want to get, like, say, the 10 nearest neighbors using your typical Levenstein or n-gram type comparison, you're going to be doing a much longer lookup than if you're just doing a locality sensitive tree search. So the KD tree is actually what makes the queries feasible in this case. And then you run into another problem with this. How do you measure the effectiveness of your neural network? When you're doing your training, for a Siamese network, you're going to be looking at generally something like contrastive loss. That doesn't necessarily, as the loss goes down, that doesn't necessarily mean your network is getting any better at the task you want to actually use it for, which in this case is finding similar strings that are similar to strings that we are inputting. So that's a little bit of a problem. And realistically, it's a problem for embeddings in general. It's very much an open problem to say, given this set of embeddings, are these the optimal set of embeddings for this data? Unless you have some task that you're going to be putting them to use for. And, once again, it can be even harder if there's not an actual right answer for the network to learn. In this case, you could have, say, the hypothetical domain tailspintoys.com, and all of these four domains here are slight modifications. Those could all be legitimate domains. And without the context, generally people recognize homoglyphs because there is a victim and a human looks at the homoglyph domain and says, oh, this is trying to impersonate this other domain here. It's a little harder when you don't have that additional context. Like, say, all you have is a domain registration. You want to know, like, is this domain that was just registered similar to one of the ones I care about? That's a much harder problem, and there's no good way to put that context into training the embedding layer, or into training your embedding network. And so, all of those are legit or reasonable homoglyphs for the domain in question there. So in order to actually decide how good the system is, came up with two different ways to measure it. So we're going to call this exact accuracy and fuzzy accuracy, or like an exact match and a fuzzy match. And the way we're measuring this is, let's say we have our set of 1 million domains that we've stored the embeddings for in this KD tree. If we generate a new homoglyph of one of those domains and we feed it into the network, is the resulting embedding the nearest neighbor of the one that we modified, in which case that would be an exact match? Or is it within the set of n neighbors for some given value of n that we care about? Like, let's say we want the 20, 30, 100 closest neighbors for this domain in the data set that we can then do some more expensive processing on. So, our usual standard of how good is something is, does it do better than random chance? So in this case, we've got 1 million domains that we've generated embeddings for, and they're sitting in this tree. If we were to query the tree for an embedding, and the embeddings were absolute crap, then we would expect, about a 1 in a million chance of getting it right. However, when we test with the Majestic Million data set, we're actually getting 11% perfect accuracy or perfect matches on this data set. And if we relax n to something like 30, that doubles the accuracy. So the numbers, that it's not nearly as nice as a lot of the numbers you're going to see today. There's no 80s or 90s. That's still way better than random chance, and it's useful for analysts to work with. And especially if you're using it for tasks like hunting, then accuracy starts getting a little less critical. The other question you run into when you're looking at things like this is, because neural networks, we all hate spending money on GPUs. Once you've got a model, can you use that model somewhere else? And in this case, this problem, to me, is something that should transfer fairly well. Generally, if things don't transfer, it's because the data from one environment is not the same as another. You might have a different computer naming scheme, different network layouts, different set of binaries present. When you're looking at something like domain names, they really don't change all that often. The overall distribution of potential domain names and how they're structured linguistically, that's kind of something that doesn't really change. So we think that we'd be able to take a model trained on, say, a bunch of internet domains and use that somewhere else. And unfortunately, we can. So what I did with this, in this particular case, was I took a model trained on the Majestic Million data set, generated vectors or embeddings for 4,000 of our internal domains, just to see how well the model worked with those, trained up a new KD tree. And it actually worked better than it did on the data it was trained on. So that had me a little suspicious at first, but thinking about it a little bit, a tree of 4,000, you're significantly more likely to get, just from random chance, you're significantly more likely to get the response you want than a set of 1 million. So that's one thing that I want to get some better numbers on, over time as we use this, is how big does the search space, how much does the search space influence the model? That's something you don't see with a lot of models. It's an interesting problem to deal with. But so that's most of what I wanted to cover today. There's still plenty of work to do, fine-tuning the approach, deciding what works best. That last talk on convolutional embeddings has me thinking about maybe trying some of that to train up or speed up training a little bit. But yeah, still the current set of results, the current results are still good enough for doing initial operational testing and work with the system. And like I said, if you're working at an organization that has a much smaller set of domains, then it's probably going to work even better for you. So, with that, any questions?